Okay, let's read on to problem 3. If 26 grams of water at 18 degrees Celsius are mixed with 49 grams of water at 70 degrees Celsius, find the final temperature of the system. So in this problem, we don't have a metal and water. We have two different amounts of water. One is cold and one is hot, and we're mixing them together. We're finding the final temperature of the system. Okay, I'm going to call it cold water and hot water. The initial, so 26 grams of water are at 18 degrees, so that's my cold water. The mass of the cold, C for cold water, is 26 grams. And it's at initial temperature of 18. So initial temperature of cold water. And I am going to use W instead, just to make it easier for myself. Okay. So cold water is 18 degrees Celsius. Okay, and I mix it with a hot water, so HW, hot water, at 49 degrees, or 49 grams, that's my mass. And the initial temperature of that hot water is 70 degrees Celsius. I know for both of these, C is equal to 4.184 joules per gram degrees Celsius. What is the final temperature of the system? So T final is what? Okay, now what do I know? Once again, the heat that the hot water loses is equal to the heat that the cold water gains, but in opposite direction, so with opposite signs. So what do I know? I know that minus hot water, the heat from hot water, is equal to the Q, the heat for the cold water. I can express these once again, each of these as MC delta T. Do not lose the sign. Minus mass of hot water times C for hot water, C for water, doesn't matter if it's hot or cold, times the T final minus T initial for hot water. Notice that I don't put the subscript for the final because the final temperatures are the same for both. Now over here, mass of cold water times C for water times T final minus T initial for cold water. If you notice, I've got the specific heat on both sides, so I can actually cancel that out. I can drop that. It will make my math a little bit easier. Now I can go in and I can plug in the values. My minus the amount of the hot water, which is 49 grams, times T final minus the initial temperature, which is 70 degrees Celsius. 70 degrees is equal to the mass of the cold water, 26, times T final minus the initial temperature, which is 18 degrees. Now I can distribute across the parentheses. So I have minus 49 times T final plus, because I have a minus multiplied by a minus, so minus times a minus makes a plus, 49 times 70 is equal to 26 times T final. Here I have a plus times a minus, so that makes a minus. 26 times 18. So I just distributed across. I multiplied each of these by the number outside, but I still kept those signs. Well, here I flipped it because I'm multiplying by a negative number. Okay, now I can do these products. Minus 49 times T final plus 49 times 70 gives me 3430 is equal to 26 times T final minus 26 times 18 gives me 468. Now that I have simplified everything, I can group the values or the numbers that have T final together and those that do not have T final together. If I take this, so 49 T final, and I bring it across the equal sign, that will make it a positive. And if I take minus 68 and I bring it on the left side, or your right side, that will make it positive. So I bring it across that equal sign. So let's do that. 3430 plus 468 is equal to 26 TF plus 49 TF T final. If I do that math, I get 3898 is equal to 75 times T final. To isolate T final, I divide both sides by 75. 75. That cancels, leaving me T final, which turns out to be 51.97 degrees Celsius. Now I can stop and think about it a moment. Does this answer make sense? Yes, because it is in between my initial values, for the hot and the cold water. It is higher than the initial temperature of the cold water, which it should be because this water gained the heat, so it increases in temperature. And it's lower than the 70 degrees, which is the hot water, which is true because the hot water loses temperature, loses heat, so its temperature drops, which it did. Okay, I will erase this. I'll do one more problem, and that will be the end of the problems from the slide. Okay, this is the last problem. A 97-gram sample of gold at 785 degrees Celsius. So I have the mass of gold at 97 grams. And then I have the initial temperature of gold at 785 degrees Celsius is dropped into the mass of water, 323 grams, which has an initial temperature, so initial temperature for water is 15 degrees Celsius. If gold has a specific heat of 0.129 joules per gram degrees Celsius, and I know that water's specific heat is 4.184 joules per gram degrees Celsius, what is the final temperature of the mixture? Okay, so I'm still solving for the final temperature. I am doing so many of these because, as I said, this is the hardest type of these kind of problem because you're working at the same time with both the heat for the gold in this case and the heat for the water. So it can be a little confusing to keep track of the units. Okay, what do I know? I know that the gold is the hot object put into the cold object. So minus the Q for gold is equal to the Q for water. I can express these in terms of MC delta T. So minus mass of gold times C for gold times T final, which is the same for both gold and water, minus the initial temperature of gold. That has to be equal to the mass of water times the specific heat for water times the final temperature, which is the same as that of gold, minus the initial temperature for water. Now that I have this, I can go ahead and plug in the numbers that I know. Minus mass of gold is 97 times 0.129 times T final minus T initial, which is 785 degrees, is equal to the mass of water, 323, times the specific heat for water, 4.184, times T final minus the initial temperature of water, which is 15. I can do these two products first. This gives me minus 12.513 times T final minus 785, I didn't change this part, is equal to this product, which gives me 1351.432 times, I don't change this part, T final minus 15. Okay, now that I have this, I can go ahead and distribute across the parentheses for both of these, which means the distributing means that I'm taking this number and I'm multiplying it by each of these values, and I keep that. So it's not a multiplication across, 12.513 times TF times 785. I multiply these two numbers, and I keep either an addition or a subtraction, depending on if I'm multiplying with a negative number or a positive number. So let's do that. Minus 12.513 times TF. Now I'm multiplying a negative number by a negative number, so that's a positive, plus 12.513 times 785 is equal to, I take this number, I multiply it by each one of them. So 1351.432 times T final. Now I have a positive number multiplied by a negative number, so it's going to be negative, minus 1351.432 times 15. So between the T final and the next number, I have either plus or a minus, not a multiplication in between. I see a lot of students that make that mistake. So you're going to either add the number without the T final, or you're going to subtract the number without the T final. Now let's do these products over here. And minus 12.513 times T final plus this product gives me 9822.705 is equal to 1351.432 times T final minus, if you do this product, this product over here, you get 20,271.48. Do the math along with me so that you are familiar with how to do this, or where I get the numbers from, okay? That way you are not lost when you do the math. Okay, now I have two numbers that have TF and two numbers that don't have TF, so I can get them to add those numbers together and those numbers that don't have T final. Now if I take this number and I cross it on the other side of my equal sign, this will become positive. If I take this number and I cross it over the equal sign, this negative will become a positive. So I will have 9822.705 plus 20,271.48 is equal to 1351.432 times TF plus 12.513 times T final. Okay, now if I do these, I will get 30,094.185 is equal to 1363.945 times T final. To isolate T final, I divide both sides by 1363.945, 1363.945. These cancel, so T final should be equal to 22.06 degrees Celsius, or 22.1. Now, let's just stop and ask ourselves, does this answer make sense? Okay, my final temperature is much smaller than the initial temperature of gold, which makes sense. Gold was really hot. It's going to be put in cold water, so it's going to lose a lot of heat. So the final temperature is going to be lower. The initial temperature of water was 15 degrees, and the final temperature is higher than that because the water gained all of that heat that was lost by the copper. Notice the temperature change. Because water has such a high specific heat, the temperature change is not that much. Look at how small the specific heat of gold is, which means that it loses heat very quickly. And you can see the difference in temperature. It's very, very large. Okay, I am going to put these up on JetNet. Put the links up. They will take you to YouTube. Look these over. And then ask any questions that you might have. We will do a blue button session or a couple of them over this material as well. So if you have any questions, you are welcome to bring them along during those sessions as well. Okay, thank you.